At the end of the lesson, you are expected to identify the different points of gradient, build an intuitive understanding of gradient-based optimization, and value the significance of gradient-based optimization. Before proceeding to a more technical and computational part of this topic, let's consider this intuitive explanation of gradient. So imagine yourself on top of the mountain. So in this illustration, for example, the green one is our mountain, and you could see here a river. So this represents our river. So here you can see a path of a river that originates from this top of the mountain. Okay, so let's add here. Okay, so that's the top of the mountain. So our understanding of gradient shall be taken in the context of this situation. So the goal of gradient descent is the same as what this river would like to reach. So this is reaching the foothill, this one, or it could be climbing from the top of the mountain, or climbing down from the top of the mountain. So this illustration shows you less hassle, smooth flow of the river water from the top. So as you could see from here, so the water just flows from this part of the mountain going to this part of the downhill. Okay, so as you could see, there are no part of this course of the river wherein water may stay, right? Okay, so we can see that the terrain of the mountain is naturally designed in such a way that the river water does not have to stop completely at any point before arriving at the lowest part or point, which is the foothill. So similarly, in the case of machine learning and deep learning, let me write that, deep learning and machine learning. Okay, this is saying we've found, or this is saying that we've found the global minimum and the optimum of the solution starting from the initial point. So remember that, global minimum and optimum. So later we will mention about these two terms. We will have that. So, but this kind of situation is not the most likely we can expect, of course. So most likely we can always expect some pits in the course of the river. Okay, let me draw something here. Okay, all right. Okay, so I'm so sure you've experienced going to a certain mountain in your area, and you've visited a river, and most likely, okay, there is always a certain pit in the course of the river wherein water can stay, right? So because the river does not just go smoothly as we expect it to be, there are parts wherein we can see some pits. Okay, for example, this is the pit of our river. Okay, so what then if there is a pit in the course of the river? So these pits, in this case we have only one pit, traps the water and stagnate it, especially in times when there is not enough running water, right? So especially when it's summertime and there is not enough supply of water from heaven or from the sky. There's no enough rain, so the water that remains here would really stagnate. So in the concept of machine learning and deep learning, we can call these pits the local minima, or local minimum if there is only one. So let me write that, local minimum. Okay, all right. So of course, having local minimum in the case of deep learning and machine learning is not really very desirable. Okay, so in our next topic, we will be discussing how to get out of these pits. So be sure to click the subscribe button below so you would be able to be notified of our future lesson. So what does this mean when we have this one? So this means to say that gradient descent is prone to being stuck in the local minimum. This depends on the topography of the terrain. So in machine learning or deep learning, we call it functions. Let me write that. Okay. It is called function. So for a very smooth and continuous flow of water, having a bowl-shaped terrain, for example this one, is a great blessing. Maybe you would ask me, what makes this one a great blessing? What makes this one better than this? Okay, especially when in this case we have a certain pit. So what is this? In machine learning and deep learning term, we call it convex function. So we are actually introducing here different terms because these are very important. So this is called convex function. Convex function. So in our future lesson, we would be able to understand more about what this convex function is, and it would be very easy for us to understand the concept, especially when we talk about applications, when we know the meaning behind the different concepts such as local minimum, the function, and this kind of function which is convex function. So let's go back to our question, which is what makes this shape, a bell shape or a bowl shape, a blessing. So this is a blessing because we are guaranteed to find the optimum. So we can never reach the downhill, for example, in this case. Okay, or even in this case, we do have the downhill. So in this case, maybe you would ask me, where is the downhill? If this is the mountain, wherein we could see the course of a river. So I'm going to use another color, right? So it's hard, okay? So for example, this is the lowest point. Okay, so we can never reach the downhill using the same speed and at the same time. Okay, so for example, if we are here in this point, this is, for example, person A, and this is from this point, this is person B. Okay, so maybe you would ask, if we're going to start at the same time, are we going to reach the same point at the same time? What do you think? Okay, so of course not. We can never reach the same point at the same time, having the different starting points, or even when we have the same starting point. So in this case, for example, this is A and this is B. So we have the same starting point here. So even if we do have the same starting point, we may never reach the same destination at the same time. So maybe you would ask me, why is that so? The reason is we may start from, again, in this case, we may start from different locations. Okay, so just like what we've drawn in here. Our speed may depend on the steepness of our location. Of course, the more steep it is, then it would be easier for us, or it would be faster for us to reach the downhill. Why? Because let's just make a review of our lessons on the law of gravity. So the law states that the steeper it is, or your location is, then it would be the faster you can reach the bottom, because the law of gravity, or the force of gravity, is stronger when you are steeper than when it is not. Okay? So our speed may depend on the steepness of our location, or in this case, it could be on our choice of speed. So for example, if we would like to go faster to our destination, we would like to use more force reaching this point. But if we would like to reach, or if B would like to reach this point slower than A, then B is not going to exert more effort than A. So that's it. So in machine learning and deep learning, we call this learning rate or step size. Let me write that. This is very important. Learning rate or step size. Okay, so it means, for example, just for the sake of our illustration, and don't worry because in our next lesson, we will be having all of these things in our computation. So, for example, letter A or person A would use only one force, but B will use two. So, who do you think is going to reach our destination in the foothill first? Of course, it is B because B is using higher learning rate than letter A or person A. So, this also means we can arrive in our location in different manner. So our starting point, and our speed can determine whether we can avoid the pits or trapped in them. Okay, so why is that? Because when the more force we're going to use, the more smooth we can glide in this part of the course of the river. Okay, so when you use less force, the more you will be sunk in this part of the pit. Okay, so because there is no greater force that's going to pull you going downward. Okay, so how should we then consider the different points? Okay, so before we proceed, please don't forget to subscribe and click the like button of this video. So let's start by saying that most deep learning algorithms involve optimization. So what then is optimization? So let's define it. Optimization is the task of minimizing or maximizing some function x by altering x. So let me write that because this is very important. By altering x. Okay, again. Optimization is the task of minimizing or maximizing some function x or fx by altering x. So altering here means we're going to change something. It's not necessarily that we're going to take it away or just pull it and then we're going to replace it with a different one. Of course, it's not like that. Okay, so optimization algorithms may not be able to find a global minimum when there are a lot of local minima present. So remember our local minimum, okay, which means the lower part. So in the context of deep learning, we may accept a local minimum even if it's not the global minimum, for as long as it corresponds to the significantly low values of the cost function. So what do I mean by this? Now, let's look at this illustration for better understanding. So you can see here, just like what we've done here. So we also have here certain course of excuse me of our river, and we have here different letters that represent different points in our course. So what does each one mean? So point C, let's start with point C. Point C is a local minimum, okay, that can perform poorly, and this should be avoided because this stagnates our algorithm. Remember the pits? So it stagnates our algorithm because it stays here, and if it does not have enough force, then it cannot go downhill. Okay, so most likely if we're going to use point C, we're going to stagnate. Our algorithm is going to be stagnated. Now, let's choose letter A. What's going to happen? So point A is our ideal global minimum actually. In this case, as far as this situation is concerned, maybe you would ask me what makes a global, an ideal choice. So as you could see, A is the lowest point, right? It's the lowest point among the 3 points. Okay, but then it is blocked by this part here. See, it is blocked by this part. So it is blocked. So this makes point A impossible to arrive at this point because again, it is blocked. So when we say global minimum, it refers to the smallest overall value of a set or function over its entire range. So let me write that. Global minimum, I think here. Global minimum. Okay. So as you can see, the point from this part going to this part is the range of our data, and this is the lowest or the smallest part. Okay, so point B, let's go to point B, is a local minimum which can perform as effective as A. Okay, as the global minimum. So this can be considered as acceptable. So what is the difference between A and B? Why, even if, again, A is the lowest one, it is not considered to be as effective, even though this is the smallest. Why is it B can be considered as the most acceptable among the three? Okay, so let's try to look at this one. So our point, for example, we're going to start from this point. Okay, so our data can just flow from this point going to letter B. Okay, and the problem is that when it reaches B, it may not be able to reach A. Why? It's because here the pit is too deep for our data to go to letter A. So even if some of our data would flow into A, it would still not be impossible to take them, because the amount of data or information that would flow into A would be lesser in comparison to the amount of information that this part of the range would be collected. That's why letter B is more preferable than letter A, right? So I think that is settled. So maybe you want to ask, will there be only one global minimum? So, well, it is possible to have a multiple global minima of a certain function. So how is that? So clearly, this happens when we have multiple the same lowest points. So for example, letter A and letter B have the same lowest point. So for example, this is 1 and this is also 1. So we have two global minima. So just like what I have said, it is also possible to have local minima which are not globally optimal. So in our deep learning practice, we may be able to encounter optimizing functions that have a lot of local minima but are not really optimal, just like in this case, for example. So they are coupled with many saddle points sometimes. So this illustration is an example of a saddle point. So what do we mean when we say saddle point? So in short, when we say saddle point, this is a point that are neither minimal or maximal. For example, here. So it is just somewhat in the middle. So it's not maximal, it's not optimal. Okay. So considering these situations, so this makes optimization a bit difficult, especially when the input is multidimensional, but of course, we can do something about them. Why do we have to study this? What is this for? Most optimization problems are regarded in terms of minimizing the function of x. Also, maximization can be processed using minimization algorithm by minimizing negative fx. So knowing the different points, we will be able to identify where to start and how fast we should be moving or going. So after all being said and done, let's try this. What are the different points to consider in gradient-based optimization? Can you picture out an intuitive image of gradient-based optimization? In what situation do we consider local minimum over global minimum? Please leave your answers in the comment section below so that we would be able to have a very rich exchange of ideas, and you and I can learn from each other, and also others would like to or who are visiting our channel. Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.